70 miles per hour, outside lane, lorries left and right. Your eyes close, your hands fall off the wheel. Every car on the road, including a £250,000 Mercedes S-Class, does exactly one thing next. It beeps. Then it kills you. XPeng built the only car on Earth that doesn't. And the engineering reason why exposes everything the European auto industry got wrong for the last 20 years. Modern ADAS is fundamentally reactive. Lane keep assist steers gently when you drift. Emergency braking fires when a sensor detects an imminent collision. Fatigue alerts flash when your eyes close for too long. But all of these systems share a critical flaw. They assume the driver is still capable of responding. They nudge, they warn, they wait. A sudden cardiac arrest gives you zero time to respond. A severe stroke doesn't announce itself. In those scenarios, every conventional ADAS system on the market today, regardless of how expensive the car is, will either brake abruptly and cause a pileup or drift helplessly into oncoming traffic. This is not a feature gap. It is a structural failure in how autonomous safety systems have been architected for the past 2 decades. The industry has invested billions in making cars more comfortable to drive. Almost nobody invested in making them survivable when the driver ceases to exist as a functional human being. That is the problem the XPeng J9 was built to solve. And the engineering behind how it solves it is considerably more sophisticated than any press release will tell you. To understand why the G9 can execute a full autonomous emergency rescue maneuver in live motorway traffic, you have to understand what is happening computationally in the fraction of a second after a driver loses consciousness. The G9 sensor stack is built around a dual front-mounted LiDAR array, generating a continuous high-definition 3-dimensional point cloud of the environment at several dozen frames per second. This is layered with high-resolution stereoscopic cameras covering all angles, millimeter-wave radar for penetrating rain and fog, and ultrasonic proximity sensors for close-range spatial awareness. Raw hardware, however, is only half the story. The critical differentiator is XPeng's proprietary Turing AI computing platform. This is the central nervous system of the vehicle, a processor array capable of running billions of inference calculations per second, fusing every sensor stream into a single coherent model of the world in real time. When the system detects that the driver has become unresponsive, through steering torque sensors, seatbelt pressure monitoring, eye-tracking cameras, and biometric feedback, the response is not a warning beep. The AI moves immediately and decisively into full vehicle authority. It activates hazard lights within milliseconds, not as an afterthought, as a deliberate communications act, signaling to surrounding vehicles that something is wrong, buying fractional seconds of behavioral change from nearby drivers. Then it begins the lane exit sequence. This is where steer-by-wire becomes crucial. Unlike a traditional hydraulic or electrically assisted rack, a steer-by-wire system has no mechanical connection between the steering wheel and the front axle. There is no column, no physical link. Instructions travel digitally, at the speed of electronics, with near-zero latency. The G9's AI can command a 2.5-degree steering correction and have it executed in under 20 milliseconds, roughly 12 times faster than an alert human driver responding to a visual stimulus. The car calculates the trajectory of every vehicle in its vicinity. It reads the lane markings, it assesses the distance and closing speed of traffic behind it, and it identifies, with probabilistic scoring, the safest deceleration corridor, hard shoulder, emergency bay, grass verge, wherever the physics of the situation allow a clean, controlled stop without triggering a secondary collision. What European manufacturers cannot replicate right now is the latency advantage XPeng has by controlling the full stack. Bosch supplies sensors to one automaker. A separate vendor writes the fusion software. A third builds the steering actuator. Each handoff between systems introduces latency, compatibility constraints, and software abstraction layers that slow response time. XPeng writes its own software, designs its own architecture, and manufactures its own AI silicon. When the camera sees a gap in traffic, the signal reaches the steering rack in a single uninterrupted digital instruction. No translation, no lag, no compromise. Autonomous emergency protocols handle the survivable scenarios, but automotive engineering exists in the real world, where not every crisis is avoidable. Sometimes a heavy goods vehicle runs a red light. Sometimes an impact is simply unavoidable. This is where the XPeng GX reveals its second engineering argument, the structural case. The GX is built on an 800-volt silicon carbide electrical architecture. The significance of this is not just performance, Moving from a 400-volt to an 800-volt system changes the fundamental physics of energy transmission through the vehicle. Higher voltage means lower current for the same power output. Lower current means thinner wiring, less heat generation, and significantly reduced resistive losses across the entire drivetrain. The electric motors receive cleaner, more precise power delivery. The thermal management system works less aggressively, and the vehicle's overall energy efficiency improves measurably at every operating point. More significant still is XPeng's Cell Integrated Body Architecture (CIB). In conventional electric vehicles, the battery pack is a discrete case mounted beneath the floor. It contributes weight. It contributes height to the floor structure, but it contributes almost nothing to the structural rigidity of the chassis. In the GX, the battery enclosure is engineered as a primary structural member. It is not bolted under the car as a secondary component, it is the spine of the vehicle. The torsional rigidity figures this unlocks are remarkable. The GX achieves chassis stiffness numbers that rival purpose-built track machinery, which has a direct impact on handling precision, NVH isolation, and crash energy management. The passenger cell itself is a combination of aerospace-grade aluminum extrusions and ultra-high-strength hot-stamped steel. The A and B pillars are engineered to resist crush loads that would deform conventional unibody structures. Front and rear subframes are designed as sacrificial crumple zones, absorbing kinetic energy through controlled deformation, redirecting crash forces away from the occupants along precisely calculated load paths. The battery enclosure includes ballistic-grade impact protection and thermal runaway suppression technology. Fire-retardant mica layers and active liquid cooling circuits are built into the battery casing specifically to contain and dissipate thermal energy if cells are crushed in a severe collision. This is not an optional safety feature, it is a designed-in structural system. The GX runs a bespoke double wishbone front suspension with a multi-link rear, a configuration that in itself is unremarkable. What transforms it is the predictive active damping system layered on top. The dual-chamber air suspension on the GX is continuously variable, adjusting stiffness independently at each corner. But the key word is predictive, not reactive. The suspension control unit reads the forward-facing LiDAR data directly. As the car approaches a pothole, a speed bump, or a surface transition, the damper adjustments happen before the wheel reaches the imperfection. The system has already measured the depth and geometry of the obstacle and configured the damper to the optimal response, up to 500 times per second. The result is a dynamic that traditional suspension engineering cannot achieve through mechanical means. Soft ride quality over broken surfaces and sharp flat cornering behavior in dynamic conditions are normally opposing demands. You tune a suspension for one or the other. The GX eliminates that trade-off algorithmically. The ride is comfort-tuned when driving straight and performance-tuned the moment lateral loads begin. This is why the anti-roll bar, a passive mechanical device designed to resist body roll by connecting opposite suspension corners through a torsion spring, becomes redundant. The GX manages body roll dynamically, in real time, with far more precision and adaptability than any physical bar can provide. The weight savings, the packaging benefits, and the ride quality improvements from eliminating that component are not trivial. Legacy automakers are still optimizing passive mechanical systems. XPeng is replacing them with software-defined active control. The automotive industry has a well-established pattern of incremental improvement. Better headlights, lighter materials, more efficient engines, more gears in the gearbox. Each generation a marginal refinement on the last. What XPeng has built with the G9 and the GX is something categorically different. It is not an iteration, it is a platform, a fully integrated combination of autonomous intelligence, structural innovation, and software-defined mechanical control, designed from first principles rather than evolved from a century of legacy architecture. The executives in Stuttgart and Munich understand this. The engineering teams in Coventry understand this. The question they are wrestling with is not whether Chinese automotive technology has reached parity with European luxury. It has. The question is whether their own organizational structures, built around supplier relationships, legacy platforms, and heritage brand positioning, can adapt fast enough to respond. The benchmark has moved, and it did not move incrementally.